Hi students, in this video we will be covering limits numerically, graphically, and analytically. We're going to split this into two parts. The first part will cover us looking at limits numerically and graphically, and then the second part we will cover the problems that are at the end of the notes and talk about the different analytical methods we can use to find limits. You will need to make use of Desmos, so open it and just follow along with the video. So for our first question, we have this piecewise function, and the question says if we trace the graph from left to right as we get close to x equals -1, what does it seem the y value will be? So imagine that we start at this open circle here and trace our graph from the left, meaning we start to the left of x equals -1, and we stop when we get very close to -1. X equals -1. It seems like the y value will be 4. The y value will be 4. Let's do the same thing from the left. I'm sorry, from the right. So now if we start at this circle, and we can actually start closer, but just to illustrate the point. So we start at 2, and we just trace all the way back to -1. We go up. We're going up to about 5.25. We'll turn back around, and then when we get close to -1 from the right, it seems the y value is also 4. So we'll write the y value is also 4. So now our third question is, what is the value of f of x when x is -1? So if we look at our function, when x is exactly -1, our y value is 4. So we'll write that when x equals -1, y is 4. Now another way of saying that is f evaluated at -1 equals 4. And our question is, what effect, if any, does the approach to -1 have on the actual function value when x is -1? So again, if we trace from the left, it seemed like we were going to be going to 4. If we traced from the right, it also seemed like we were going to be going to +4. And then the actual value didn't seem to have any impact. We were going to the same direction. So both directions gave the same y value. Okay, maybe good to know. So you pause the video and you do this for x equals 2 and write down anything that you observe. Okay, so if you're rejoining me from pausing the video and doing the same process for x equals 2, let's see what we arrive at. So let's erase the graph for the -1 stuff and start back over. So if we approach 2 from the left, meaning we're drawn on the left part of the graph, close to 2, so we'll start at like 1 point something. And as we move to x equals 2, it seems that the y value should be -1. So we'll write when coming from the left, the y value seems to approach -1. And then if we do this from the right, so we'll get, again, very close, but not exactly to 2. So if we trace this from the right and head to 2, it seems like our y values want to get very close to 5. So we'll put here, we'll put some quotes. So we'll say when coming from the right, the y value seems to approach positive 5. Let me make sure that was 5. Yep, positive 5. So now if we look, and so then when we look at exactly at x equals 2, so when x is exactly 2, the y value is, what is that y value? It is 3. The y value is 3. So would you say the limit existed at this point? So we get 3 different values. So we have, when we approach from the right, we get 5. When x is exactly 2, we get 3. And when we approach from the left, we get 2. I would say here the limit does not exist. And maybe we'll come up with a reason why. And so lastly, do this same process for x equals 4. So when we approach 4, then when we approach 4 from the right, and we can do this quickly, if we approach 4 from the right and left, it seems as if our y values target the value of 2. So we can say when approaching, we'll abbreviate approaching, actually we won't. So when approaching from the right or the left, the y values approach, I can't remember the value actually. Let's go back and look at the graph again. The y values approach 2. But now if we look at the graph, we have an open circle at the point 4, 2. What that's going to mean is that f of x isn't defined at 4. So f of x is not defined at x equals 4. Now the question is, does that have any impact on what our function values approach? So if we get very, very close to 4, we can actually zoom in. So we get very, very close to 4. It actually doesn't impact what our values are approaching. So we'll say f of x not being, well, we'll say f of x being undefined. F of x being undefined at x equals 4 does not impact values, and by values we mean output values close to x equals 4. So in these 3 examples that we use, in one case the limit and the function values were the same thing. In the second example, the limit didn't exist because the left and the right values approach different things and the function value was different. And in the last example, when x was approaching 4, the left and the right parts of the graph agreed to a common meeting point, but the function wasn't actually defined. In the case of the first scenario and the third scenario, the limit existed both times. One time the function value was defined, the second time the function value was not. So the existence of the function value has no impact on if the limit can or will exist at a particular point. So now if we did this analytically, we could consider the function f of x equals x squared. And we want to find the limit when x equals 2. And we're going to suppose our dx, our delta x, is 0.25. So that's going to mean that we're 0.25 up from 2 and 0.25 down from 2. So because delta x is 0.25, we're looking in the range of, we're going to say our x's are between 1.75 and 2.25. And so then we want to see the range of our y values. And to do that, we can just go over to Desmos. So we're going to put in f of 1.75. That's going to give us 3.0625. So 3.0625, and then actually I'll show you what we're doing. So we'll put as a point on the graph 1.75 comma nope, not functions. Then f, nope, I do need a comma though, comma f of 1.75. So then we'll like zoom in there. And then we'll put that point, we'll put a label there and we'll call it, I don't know, A. So we'll call it point A. And then we're also going to put 2.25 comma f of 2.25. Oh, f of 2.25. Close that parenthesis. And we'll put a label on, we'll call that point, doesn't really matter, call it point B. Oh, not slider though. No. So move over, delete, we'll add a label down here and call it B. Okay, so if we look at our graph, let's actually put one more value. We actually need the value of 2.25. So f of 2.25. Why is it not giving me parentheses? F of 2.25. And that's 5.0625. So 5.0625. So that's the range of our output values. They're somewhere between 3.0625 and 5.0625. So now if we narrow our range a lot, so instead of using 0.25, we're going to use 0.1. So now we're saying our x's are either 0.1 greater than 2 or 0.1 less than 2. So we're saying our x's are between 1.9 and 2.1. And we want to see what happens to our y's instead. So let's go back over here and check this again. And instead of, we said so 1.9, and we'll change that to be f of 1.9. And then we'll change this to be just 1.9. And here, instead of 2.25, we'll make that 2.1 and f of 2.1. Well, I didn't put a decimal, 2.1. There we go. So now, also we want to change this to 2.1. So now our y's are between 3.61 and 4.41. So our y's are between 3.61 and 4.41. Now you do this process for 0.0001. Pause and come back. All right, so if you're rejoining me, if we use 0.0001, then our x's are between 1.9999 and 2.0001. Let's see what that looks like and see if we can get a good read on what's happening. So we said 1.999 and f of 1.999. We'll make that f of 1.999. And so now our y's are between, I already forgot the value, 3.999, 3 nines and a 6. 3 nines and a 6. So our y's are between 3.996, and we'll try this also with 2.001. 1, 2, 3. 1, 2, 3. And 1, 2, 3. We'll zoom in really, really closely. So now we can see if we zoom in a ton that as we approach 2 from the left and right, our y values seem to be approaching the same value. So what was that value? It was 4.0004, 3 zeros and a 4. So 4.0004. And so what do we notice about the output values on either side of f of x? As x approaches 2 in either direction, the function values approach y equals 4. And that actually makes sense because we know that f of 2 equals 4 if f of x equals x squared. So this is a numerical approach to finding the limit. Now, obviously, you need a calculator to do these calculations, but that's kind of the same process. So to cut down on the length of the video, let's skip straight to this step where we're very close to x equals 0, so like 0.001. So that's going to mean that our x's are in the range of, and we're finding the limit when x approaches 0, so our x's are in the range of negative 0.001 and positive 0.001. And since we have this piecewise function, then that's going to mean that our y values are going to be in the range of, well, let's see what happens. So if x is negative 0.001, we need to use this part of the piecewise function because that's when x is less than 0. So we're going to have negative 0.001 plus 2, which is equal to 1.999. And so then when x is equal to 0.001, then we're going to get 0.001 plus 4, which is 4.001. So now imagine we got even closer, like we added a 0 to, we added one more 0 to our decimal place. Then we would next get 1.9999, and then we get 4.0001. If we keep adding zeros, we keep adding nines, and eventually the left part of the graph is going to approach 2, and the right part of the graph is going to approach 4. And we say something like the values from the left would approach 2, and we'll say the values from the right would approach 4. So this limit doesn't exist because the values from the left don't approach the same thing as the values from the right. So here we would say something like the limit as x approaches 0 does not exist. So if you had to come up with your own definition for when the limit exists at a point, how would you define it? Pause, write some stuff down, come back and compare it to my definition. All right, so for me, I would say the limit exists at a point when the limit from the left equals the limit from the right. Now, mathematically, the way we would say this is, so when we're talking about the limit approaching a value, we mean just any value. So we're going to say the limit as x approaches c, and c is some arbitrary number. And so if we're approaching from the left, this notation means approaching from the left. So if the limit as we approach c from the if the limit as we approach C from the left equals the limit as we approach C from the right, and so this notation means approaching from the right. I'm going to abbreviate that since we already wrote one definition, approaching from the right. And if those two things equal, we get some limit value called L. And L is not any, L is some real number. And so all we're saying for the limit to exist is the limit from the left equals the limit from the right. And so even more is the limit as x approaches C for f of x exist on if and only if and only if the limit as x approaches that value from the left for the function is equal to the limit as x approaches that value from the right. All right, so that's going to conclude our video for just the theoretical parts of limits. This next video, we'll talk about doing analytical methods to find limits.